People trickling in. So it's really great to have Alex Wein here virtually talk about the new result on tensor decomposition.
Great. Yeah, thanks so much. Thanks for the invitation, and thank you all for being here. Yeah, please feel free to stop me if you have any questions. You know, I have a second monitor so I can see anyone if you have your video on, and I can see the chat as well. So yeah, there should be plenty of time for questions and so on. So great, let me get started then. So this talk will be about tensors. So what is a tensor? So you're already familiar with an order 2 tensor, even if you don't know it. So an order 2 tensor is just a matrix. So an n by n array of numbers. An order 3 tensor is just an n by n by n cube full of numbers. And we can write the entries, you know, now indexed by I, j, and k. And of course, we know that for a matrix, we have this notion of a rank 1 matrix. So if you take some vector v, if v is some vector, you can form this VV transpose as a rank 1 matrix, you know, and its entries are defined like this. And similarly, there is a notion of a rank 1 tensor, right? So let's say we have this order 3 tensor. Again, if you take some vector, we write the third tensor power of the vector to now be this order 3 tensor, you know, defined this way. Okay, so this is sort of a natural generalization of VV transpose. You can also have tensors of order 4 and above and so on, but this talk I'll mostly talk about order 3 tensors. Okay. So this talk will be about a problem called tensor decomposition. So tensor decomposition is a very basic algorithmic primitive that shows up in a lot of different machine learning type of applications. So here are just a few examples. And basically, okay, why do tensors show up in all these different areas? One main reason is because of the method of moments. So if you have a bunch of data and you compute all of the joint order 3 moments of this data, you know, this would be an order 3 tensor that we could now hope to analyze to learn something about the original data. Right, and so this, you know, type of idea has been hugely successful in giving lots of different algorithms. So let me actually define now the tensor decomposition problem. So the problem is this. So I'm going to give you a rank R order 3 tensor, right? So it's an n by n by n array of numbers. And when I say rank R, I mean that it's the sum of R different rank 1 terms. Okay, so these AIs are called the components. So each AI is a vector, and I give you the sum of you know, the appropriate rank 1 tensors, right? And given this, given just T, your goal is to recover the individual components, you know, up to sort of the inherent symmetries of the problem. So of course, you can't figure out which component was called A1 versus A2 versus A3, but you can hope to you know, recover this collection of vectors up to reordering. And to make our lives a bit easier, we're going to make an additional assumption even, that let's say the components are actually drawn randomly. Let's say I draw them all just with IID Gaussian entries. And so the goal really is now to successfully decompose the tensor with high probability.
So for the worst case, it's NP hard.
Yeah, that's exactly right. So in the worst case, this problem would be NP hard. And so I'm going to be more interested in thinking about sort of average case problems where the components are random, where there's also been a lot of work and sort of you know, smooth analysis type of results where if the components are sufficiently generic and you know, various other assumptions. But yeah, you basically can't hope to do anything without knowing some assumptions on the components. Yeah.
How small is R before it's NP?
Okay, that's a good question. So in the worst case, how small should R be? Yeah, it's true, because if if R is just 1, of course you can do it. Yeah, I don't actually know the answer to this. That's a great question. Does anyone out there happen to
Guess
know?
3. That's my big guess, but
Oh, R equals 3.
Well, one way is to matricize, right? To flatten it.
Yeah, that's true. Right. So a lot of algorithms work when R is smaller than N, but you need some sort of weak assumptions, like that the components are linearly independent or something. So yeah, I don't exactly know the answer, but that's a good question.
okay, thanks.
But yeah, so I'll get to this.
So somebody put in the chat.
Yeah, for constant R, it's polytime.
Yeah.
Yeah, probably because you can kind of guess all
Yeah.
the possibilities or something like that.
Anyways,
But yeah, my focus will mostly be on the case where the rank is quite high. So we'll try to be, working when the rank is as big as possible, and we'll see now sort of how large we can hope for that to be.
and we're over the reals.
Yeah, that's right. So all the tensor entries are real numbers.
Okay, thanks.
Yeah, good. Thanks for the questions. Okay, so what's sort of known about this problem already? So there's actually like a ton of algorithmic results for this. And here's just a couple of the sort of state-of-the-art ones. So some of them are using SOS, which stands for sum of squares. So the sum of squares hierarchy of semi-definite programming. So a bunch of algorithms use this, and also some sort of faster spectral methods, meaning you take your tensor, you build some kind of matrix out of this, and then you look at its eigenvalues or eigenvectors. But the best known polynomial time algorithms, work when the rank is as high as this threshold n to the 3/2. So this was first achieved by Ma, Shi, and Stoyer. But on the other hand, sort of in principle, information theoretically speaking, you could hope to decompose the tensor even at a much higher rank, when the rank is something like n squared. Right? This is because the decomposition is unique at this point. And so in principle, if you're willing to sort of do some brute force search over all possible decompositions, you would be able to find it. But we don't know, a fast algorithm or efficient algorithm. Right, so here's kind of the picture of what's going on here. We have these different regimes depending on the rank R. Right, so as we increase R, we're making the problem harder. So for small rank, it's easy in the sense that we know a polynomial time algorithm. Then there's this regime that we call hard, meaning we don't know a polytime algorithm, but in principle, the problem is solvable. And then finally, the impossible regime means there's just no hope to succeed at all.
If I'm in the impossible regime, but I'm okay with some kind of approximate solution, is there anything interesting that might happen?
Yeah, I mean, I think the issue with the impossible regime is that the decomposition isn't unique anymore. So there's actually many different possible decompositions that I suspect are all quite far from each other. And so you somehow need like more information about the real one if you can hope to find it. Does that make sense?
Yeah, thanks.
But what about just decomposing? If I don't care about getting exactly the same solution, I just want any decomposition.
Yeah, good point. Right. So let's say I don't require to find actually the planted decomposition, but just any one. Yeah, that's a great question. I don't know the answer to this. I suspect it might actually become easy once the rank is, once you get into this impossible regime, there's actually like a ton of different ways you can do it, but I don't know for sure. Yeah. Yeah, good question. So the main, question I want to sort of try to address here is, is this hardness inherent? Right? Might there actually be a better algorithm that can decompose tensors up to rank, say, n squared? If so, we would love to find this algorithm. But on the other hand, if there really inherently, does not exist a polytime algorithm in this regime, we'd like to understand why or have some evidence for why we think this problem is actually hard, so that we don't indefinitely waste our time looking for better algorithms. Okay. And so this notion is not really specific to tensor decomposition. This is something that people call statistical computational gaps. And really they show up in all kinds of different problems, not just this one. So a whole bunch of different problems kind of from high dimensional statistics, sparse PCA, finding kind of community structure planted in random graphs and so on. Many different problems, are believed to have kind of this sort of hard regime. Here's one, I'll give you one more example of such a problem. This is like one of the sort of most canonical and famous ones called planted clique. So the idea here is that we take a random graph, so gn 1/2 means n vertices, each edge occurs with probability half. But then I pick k vertices at random and plant a clique there, meaning I connect all of those k vertices to each other, and the goal is to find that clique. Right, so in this example, we have a random graph on 8 vertices. I've picked 4 of them and connected them all to each other, and your goal is to try to find those 4. So I'll give you a second to look at it, but here's the answer in this case. And so this, also has the same type of picture emerging, where here now we're plotting k, the clique size. And so as the clique gets larger, the problem gets easier, right? If the clique gets really large, at some point you can easily pick it out just by using the degrees of the vertices. But we similarly have kind of this elusive regime in the middle that's conjectured to be hard. Okay. And one of the, the issue with this whole kind of area is that we don't really have hardly any tools from kind of classical complexity theory to handle these kinds of things, right? NP hardness is really a statement about hardness on worst case instances. And here we care about cases where the input is drawn from some distribution, right? So the maximum clique problem is NP hard, but still you can solve planted clique sometimes depending on the distribution of inputs. Okay, so what are we going to do though? We still would like to have some way to prove hardness about these kinds of problems. And in recent years, a lot of frameworks for this have emerged that have been very successful. So one thing people do is reductions from planted clique. So if you believe that this planted clique problem is hard, people have been able to formally relate this to other problems. So if clique is hard, then this problem also must be hard. A separate approach is also lower bounds against restricted models. So proving that certain algorithms fail or that certain classes of algorithms must fail in this hard regime, giving evidence that at least sort of our known approaches are not going to work there. And then finally, there's other approaches that are more kind of geometric in nature, looking at kind of structural properties of the solution space that potentially suggest hardness for certain kinds of algorithms. Okay, is this clear? And so I should say that, this has been really successful in recent years. We now, for like all of these problems listed here and a bunch of other ones, we actually do have some kind of lower bounds that, of these types. And we have sort of a pretty good understanding of when these problems are hard and what makes them hard and so on. But this tensor decomposition problem I mentioned is sort of one example where really we have nothing so far. And so I want to spend a bit of time telling you kind of what's different about this problem and what makes it a bit more difficult. So, let's say we want to try to prove some kind of lower bound for tensor decomposition, right? Some evidence for why this hard regime is actually hard. So for a start, which of these lower bound frameworks should we try to use? maybe the first one we could try that I mentioned is reductions from planted clique. Unfortunately, this kind of seems out of reach of current techniques, although it would be great if someone can prove me wrong. But the existing reductions we have go from planted clique to another problem that has kind of a similar signal plus noise structure. And tensor decomposition sort of doesn't have that same structure.
So what about something like Figes hypothesis? I guess that doesn't work either.
Okay, to take some kind of average case, some other kind of average case like assumption or complexity, cryptographic assumption or something. Yeah, like
Figes hypothesis.
Yeah, so Figes is specifically about KSAT, right? About
Yeah.
Yeah, right. That's a good idea. Like, my impression is that there are very few of these kinds of reductions known. But yeah, I mean, it's a good question. But basically, I don't know.
Mm-hmm.
And yeah, for the most part, it's people have had, I think, a hard time relating relating any sort of standard conjectures to these kinds of average case statistical problems.
Thanks.
Okay, so I talked also about these kinds of restricted models of computation. So you can think about, some powerful family of algorithms, try to at least prove that those algorithms can't solve this problem. And so one that's kind of popular is the statistical query model, but that's not applicable here because it's only applicable to situations where you are observing IID samples from some distribution and trying to learn that distribution. Another very successful one is sum of squares. So sum of squares is this hierarchy of semi-definite programming approaches. And sum of squares lower bounds are sometimes considered kind of a gold standard for hardness in these kinds of areas. But one thing to be aware of is that sum of squares lower bounds are really about hardness of what's called a refutation problem. So refutation is the problem of algorithmically coming up with a proof of something. For example, proving that a random graph has no large clique. And so the decomposition problem is not exactly a refutation problem. It's more like a recovery problem where we're trying to find some planted structure. And so, my light's just turned off. But in general, hardness of a refutation does not actually imply hardness of recovery.
Sorry, I hate to keep bugging you, but I have a question again.
Yeah, great.
So like so people did prove the sum of squares lower bounds for planted clique, which does rule out some kind, certain families of algorithms. So do you consider that to be useful also for this problem? Like you could, do it in a similar way, have a random instance that does have a rank R decomposition and refute, show it's hard to refute the fact that it, the negation of that.
Yeah, right. Great question. So yeah, good. So there is a sum of squares lower bound for planted clique. So yeah, I mean, one sort of subtle issue there is that, strictly speaking, this shouldn't really be thought of as a lower bound against finding the clique. It's really a lower bound against certifying that there is no clique or refuting the existence of a clique in a random graph, which is a problem that's related, but formally not.
But if you have an algorithm that's correct, then on the negative ones, it'll have to, the run of it will be like a certificate. So at least
I guess there is a refutation problem that is associated to this, which is you're trying to prove that there is no low rank composition, but it's not the same thing.
But I'm just saying that if you have an algorithm that finds,
yes.
then you a run of the algorithm on a graph without a rank or decomposition will be the
No, but the algorithm is only
Not
required
sure.
the algorithm is only required to succeed with high probability. So if
That,
it
yeah,
does,
so that's the issue.
if
I
it
guess.
doesn't find,
Yeah, so that's the issue. I
you
guess
cannot
it's
say
it's the algorithm's randomizing, yeah.
Yeah. So refutation is actually like a, a formally harder problem than just like finding the planted structure. So just because refutation is hard, it doesn't actually mean you should necessarily believe, finding the thing is hard. And like this paper gives kind of an actual example where there's sort of a gap here. But yeah, there certainly are some interesting sum of squares questions you could ask that are related to this problem about hardness of certifying, rank or things like this. Yeah. Yeah, great. Thanks for all the questions. Okay, and another approach I'll briefly mention that's also interesting is looking at sort of optimization landscapes. But again, the decomposition problem is not exactly an optimization problem, so we would have to choose, what function are we going to try to optimize in order to solve decomposition. So certainly there are some natural choices that would be interesting to look at. But there's also been sort of this great line of work recently that has, a theme that has emerged here is actually that for, say, planted clique, the natural optimization problem you might try in order to actually find the clique actually doesn't work, is actually suboptimal. So if we pick one particular optimization problem and try to study that, we have to be careful that maybe there could be a better one out there too. All right, so this is all to say that, all these different approaches are, exciting and interesting, and I think there's a lot of like great interplay between them and, understanding how they all relate and so on. But the framework I'm going to talk about today is called the low degree polynomials framework. And this one I feel sort of most directly will address the decomposition question. Okay. So, oh, is that another question or no?
No, we just laughing at your slide.
Okay, sure. So a couple more, difficulties of, what makes this tensor decomposition problem a bit harder to, or more difficult to analyze than some of the existing problems like planted clique. Okay, one issue, which is not too much of an issue, is the issue of symmetry. So, planted clique has one very concrete goal, right? We need to find this one specific clique that's planted there. Tensor decomposition, you have R different components, they're all kind of interchangeable. And so if we're asking to find one of these components, there's a question of, which one are we supposed to find? So algorithms need to break this symmetry somehow. But I think by far the most, serious issue, or the real reason why this problem is harder than the existing ones, is this reason, because basically all the existing lower bounds we have against all of these types of frameworks, be it SQ, SOS, low degree, and so on, basically all of them are implicitly leveraging some kind of hardness of testing between some planted distribution versus an IID null distribution. So let me explain what I mean by this in the case of planted clique. So, okay, remember planted clique has some regime of clique sizes where we believe it's hard. And we do have a bunch of lower bounds here. So including, all of these things really, SQ, SOS, and low degree. And what all of these things are doing is they're really saying, well, the reason it's hard to find the clique is actually because it's hard even to tell whether the clique is there or not. That is, it's hard to distinguish between this planted clique distribution of graphs versus just a GN1/2 without a planted clique. Right, so if I give you one of these two graphs, you can't even tell which one it was with high probability. Does that make sense? And so on a technical level, really all the existing techniques we have are kind of, leveraging some kind of hard testing problem of this form, where crucially the null distribution has independent coordinates, right? So here the edges are independent. Right? So luckily for planted clique, this testing problem does actually turn out to be hard in this entire regime, which lets us sort of say that finding the clique should also be hard there. Now, what happens for tensor decomposition? Well, you could try the same thing, right? Let's think about, can you distinguish between a rank R tensor versus an IID Gaussian tensor, say? The problem is that this distinguishing problem actually is not that hard. It has sort of a different threshold. It's hard only when the rank is bigger than n cubed, whereas we would hope to show that decomposition is hard when rank is bigger than n to the 3/2. Okay, so if we want to prove this result, we're not going to be able to do it by leveraging this type of testing hardness. And that's kind of really why we need some new techniques here. Does that make sense?
Why is it easy? Are you going to tell us why it's easy when R is small?
Yeah, so the reason this is easy is basically just because some low order statistics of these two distributions are not the same. So there's actually kind of a degree 4 polynomial that has a very different value on one than the other. It has to do with sort of, looking at taking 4 tensor entries that kind of form a double cover and multiplying those together. And these will do something different in the low rank tensor versus just a random tensor. Does that kind of make sense?
Yeah, yes, yeah, vaguely.
Great. Any other questions?
What about testing between two tensor in which one of the two you add one component to the R?
Yeah, this is a great question. Yeah, so this testing problem, I suspect, would have the same threshold as actually decomposing. Now, analyzing this testing problem is not something we can do from prior work. Like the existing techniques really require one of the distributions to have independent components. But I think actually that using the strategy I'll tell you today, it should be possible to analyze that problem as well. But I haven't actually done this yet. Yeah.
Thank you.
Great. Other questions? Okay, so that's a sort of maybe enough high-level philosophical discussion. Let me tell you now more precisely what actually the main results are. So the first thing I mentioned is this issue of like breaking the symmetry between the components. So I'm actually going to look at a slightly different model. We can call it largest component recovery. So let's actually consider a tensor where it's again rank R, but one component is slightly larger just by a factor of 1 plus delta. So delta can be, say, an arbitrarily small constant. Okay. And the reason for this is to break symmetry among the components, because now our goal is we're going to ask the algorithm to specifically find A1, right? To find the biggest component, just so that the algorithm has, one precise goal in mind. And in fact, okay, we want to recover the whole vector A1, but really it suffices to think about just recovering the first coordinate of A1, right? So we'll call that A11. And the reason for that is just because if I had a way to find the first coordinate, I could, do the same thing to find any other coordinate I like just by the symmetry of the problem. And then one sort of, simplifying assumption I'm going to make is that we're going to think about the model where the AIs are, random from the hypercube. Right, so each component has plus or minus 1 values at random. This is mostly just kind of for technical convenience. Really, the same results should hold if you replace this by Gaussian or, I don't know, uniform on the unit sphere or, various other reasonable things. Okay, so, hopefully this new problem feels, kind of natural and important. But let me kind of emphasize, how exactly is this new problem related to the original task of decomposing? Right, so we're going to try to prove some hardness result for this new problem. what does that tell us about the decomposition problem? So one thing we can say is that if this problem is hard for all polytime algorithms, say, then this also means, this also implies hardness of a related decomposition problem written here at the bottom. So this is a problem where I give you a rank R tensor, where again, the components are random, but now all the norms of these components are potentially slightly different, and these lambdas are kind of arbitrary, although within a small interval. All right, so this is just a slightly more kind of robust version of the tensor decomposition problem that, you would hope that, if we could solve the version where all the lambdas are 1, you would hope to also be able to solve this version. And does that make sense why hardness of the top problem implies hardness of the bottom one?
In the bottom one, do you know the lambdas or do you also have to learn the lambdas?
Yeah, let's say you also have to learn them. I mean, I think it probably shouldn't matter either way. Yeah. Yeah, so let's define, decomposing here as learning both the lambdas and the A's. And so the idea here is just that, so let's, if the top problem is hard, we want to argue that the bottom problem is hard. So let's do the contrapositive instead. Let's suppose I could solve the bottom problem. How would I use that to solve the top problem? Well, I just try applying this algorithm. This algorithm will actually recover all the components, and then I just output the largest one. Okay, so that's all. So it's not like a deep statement, but I just wanted to emphasize sort of the connection to decomposition. Does that make sense?
Yeah. Yes.
Yep.
Okay, so here then is the main result. So I'll tell you the main result, and at the same time, I'll sort of tell you this low degree polynomial framework that I've mentioned earlier. So the class of algorithms we're going to think about are going to be multivariate polynomials in the entries of the tensor. Right, so remember, we're observing this tensor, this n by n by n tensor, where one component's a bit larger than the rest. So this thing has, n cubed different variables, and we're going to think about multivariate polynomials in all of those different n cubed variables. Okay, we're going to think of that as sort of the algorithm. And what does it mean for this type of algorithm to succeed? Well, we're just going to think about mean squared error. So the degree d mean squared error is defined to be, find the best possible degree d polynomial and take its mean squared error between, between the polynomial's output and the true, A11, the thing we want to recover. Is that okay? And so here's the theorem. For any fixed constants here. So the first bullet point is about the easy regime, right? This is when the rank is small. So the regime where we do know that you can decompose tensors. Well, there is also an algorithm of this form, a polynomial of degree log n that achieves basically perfect mean squared error. And on the other hand, in this hard regime, when the rank is big, in the regime where we don't know an algorithm, we can actually prove that any polynomial, even of fairly high degree, like n to a small constant, is going to be trivial, right? So mean squared error of 1 means you're basically doing nothing. So if you output 0, you get a mean squared error of 1. Okay. So we're kind of we're proving this kind of phase transition for low degree polynomial algorithms that occurs at the same place as sort of this conjectured transition for polytime algorithms. Okay, so in the next slide, I'll kind of tell you a bit more about how to interpret this or why this model is interesting. But does this mathematical statement make sense?
I should have asked this earlier, but I don't see why when you have the version with the deltas in there, with that lower bound implies the lower bound, when the AIs are just random without the deltas. Like for the original.
Oh, are you talking about the statement on this slide that this top problem, hardness of this problem implies hardness
No.
of the bottom problem?
No, that makes sense. I don't understand why hardness of the bottom problem implies hardness of the one without the lambdas, when the lambdas are all one.
Oh, it doesn't. No, this is not a formal statement.
Okay.
So here we've, maybe cheated a little bit.
Okay.
Yeah, so that's a good question is, maybe this is like a more kind of robust version of that problem. If we really wanted to directly attack that problem where there are no lambdas, maybe one way to do it would be this idea that was brought up a bit earlier about testing, rank R versus rank R plus 1. You could show that hardness of that problem implies hardness of decomposition, even in the case where all the lambdas are 1. Because if you were able to decompose, then you would know the rank and you would be able to tell which case you were in. Does that kind of make sense?
Mm-hmm.
Great. Yeah, thanks for the question. Great. Other questions about this? Okay, so let me kind of briefly try to tell you why the previous result is kind of meaningful, or why are we looking at this class of low degree polynomials, right? So this is not something that we're doing here for the first time. This is kind of a framework that's been around for a few years now and has been kind of successful at capturing these statistical computational gaps and so on. So one thing to note is that a bunch of different algorithms can actually be captured by a logarithmic degree polynomial. So this includes a wide class of kind of spectral methods, meaning doing some kind of power iteration on a matrix. AMP is approximate message passing. Also local algorithms on sparse graphs. And various other simpler things like counting triangles and graphs and so on. So these polynomials do have kind of a lot of expressive power. And so one way to think of this approach is that it's, a concrete lower bound that can be used to rule out certain known approaches, like spectral methods and so on. And really this class of approaches we're ruling out, it seems to include kind of the state-of-the-art methods, or the best things we know for a lot of these kinds of statistical problems. Because as a result, like for these problems I mentioned before, like planted Klieg and sparse PCA, and so on, for a big list of all these statistical problems, we now know the low degree polynomial threshold, and this actually does coincide with, the best known polynomial time algorithms. And so on the flip side, if we're able to rigorously prove that no low degree polynomial works, this kind of gives us a good reason to believe the problem is inherently hard, or at least that we need to sort of do something quite different from what we've been doing already in order to pass that barrier. There are some counterexamples, admittedly. Like there are some cases where there's an algorithm that beats low degree polynomials. Low degree polynomials fail, but some other algorithm works. So a few examples of this are Gaussian elimination or lattice basis methods, usually algorithms that are kind of quite algebraic in nature. And the downside of those types of algorithms is that they tend to be very brittle and not robust to really any amount of noise. And so if we really care about sort of problems that are sort of noise robust, like as we do maybe in a lot of machine learning type of applications, I think the low degree threshold really is meaningful, arguably even more meaningful than sort of the true computational complexity in some sense. Is this okay?
Mm-hmm.
And so this framework of analyzing low degree polynomials, existing results kind of fall into three different classes depending on the types of problems you're looking at. So a lot of people have looked at sort of testing problems, distinguishing two distributions, also, estimation problems, which is recovering a planted structure. And finally, optimization. Optimization means, like, for example, I give you just a totally random graph and you need to find the biggest clique possible, right? So there's no planted structure. We're just optimizing a purely random function. Okay, and so, the framework's kind of versatile and can handle all these different problems, but the techniques for proving the lower bounds are quite different in these three cases. And then finally, maybe one more reason to sort of care about this framework is that there have been some connections to circuit complexity. So at least in some cases, these types of lower bounds can imply certain circuit lower bounds. Yeah, and this idea maybe has not yet even been kind of fully explored. Okay. Any questions about that? So yeah, okay, so that's sort of the philosophical discussion. So for the rest of the talk, I want to try to tell you a bit about how the proof works, unless there are any other questions before we dive into that. So remember, here's the main result. So the first one I want to tell you is about the easy regime, which is also kind of the easier of the two statements to prove. So here I want to convince you that for the low rank tensors, there is actually a polynomial that can sort of estimate this component that we're looking for, the largest one. Okay. So I'm mostly going to focus on the lower bound, but I'll give kind of a brief overview of this one as well. So the idea is based on something you can call spectral methods from tensor networks. So this is sort of an idea that underlies a lot of the best known algorithms for tensor decomposition. And kind of how it works is that the same way you can multiply two matrices together, you can also multiply tensors together. But because these tensors kind of have three modes instead of two, there's a lot of freedom in different ways you can actually multiply them together. And so there's these things called tensor network diagrams that sort of specify how you're actually going to take a bunch of different copies of your tensor and sort of connect them up in a way to multiply them together. So roughly speaking, a lot of these existing algorithms basically take the input tensor, build some kind of tensor network out of this, and this produces some big matrix. And then you can try to use the eigenvectors and eigenvalues of this matrix to solve the decomposition problem. And so in this case, the polynomial that achieves this estimation guarantee is kind of based on the same flavor of idea. So it's basically take your tensor, connect it up to itself in sort of a big random tensor network. And this outputs outputs a vector, and this vector will be close to the A1 that you're looking for. I won't kind of try to get into too much of the details of exactly how these, how this is defined. But let me just say that, this kind of illustrates, another reason why the low degree framework makes sense, or why it makes sense to prove lower bounds against polynomials here, is because the existing methods, are at least morally speaking, doing these kinds of things that can be expressed as low degree polynomials. Although the existing work does not literally give you one single polynomial that works. These are more like multi-stage algorithms, but can be adapted to give you one single polynomial. Does that make sense? And one caveat here, I guess, is, you might be wondering how exactly does this relate to polytime algorithms? Well, we've shown that a logarithmic degree polynomial exists. This actually doesn't imply a polynomial time algorithm because the number of terms in this polynomial is like n to the log n. And so if you sort of naively evaluate it, you would get something of this runtime. So as is this algorithm implies only a quasi-polytime algorithm, I'm almost certain that a polytime algorithm, also exists for this largest component problem just by adapting the previous results. But the focus here really is on proving the phase transition for polynomials. Okay.
Yeah, question, sorry. So what happens if you use a smaller network, for instance, like in Hopkins, Schramm, etc.? There, I think, was a thing with 2 tensor, and then, yeah, similar to that. I don't remember whether it was.
Okay, so this first paper, Hopkins, Schramm, Stoyer, is based on this first tensor network. So that one only succeeds up to a degree, rank being like n to the 4/3. But okay, basically the difference between the prior work and this. So the previous work, it takes a constant size tensor network, turns that into a matrix, and then looks at the eigenvalues of this, eigenvectors of this matrix. Which, you can kind of think of the eigenvector part as doing some kind of power iteration, which involves connecting this network up to itself a bunch of times or something. But here since I wanted to really prove that, just that there's one single polynomial that works, this is more like a one-shot thing where you're not building a matrix and doing any eigenvectors. You're just going to take one big logarithmic size network. So this turned out to be kind of more convenient to analyze if the goal is to, have one single polynomial that works. Does that make sense?
Okay.
Okay, great. So in the remaining time, I'll try to talk about the lower bound. So to tell you about the lower bound, let's just talk about a very simple scalar version of this problem. Right, so instead of tensor decomposition, let's just observe a scalar random variable t that's the sum of a bunch of unknown scalar, plus or minus 1 variables. And the goal is I give you this t, and your goal is to estimate a1. Right, so this is like a very silly problem that doesn't even really make sense because you can't hope to solve it because you can't break symmetry among these and know which one is the a1. The purpose of this is not that this is an interesting problem. The purpose is to illustrate the proof technique in the simplest possible setting. And so it turns out that, the same technique that will kind of work here can also be extended with more work to the true tensor decomposition problem that I talked about. Okay, so we're going to try to prove this lower bound anyway, even though it's silly. So originally I stated things in terms of mean squared error, but really it suffices to think about this correlation. So the thing we're trying to show is that no matter what degree d polynomial of t I take, it cannot have very good correlation with a1. Right, so here's f of t. F of t is just some polynomial in t, right? Everything's just scalars here, so this is just a polynomial. And we'll write f hat for the coefficients. Right, and so this normalization is just here so that you don't gain anything by multiplying your polynomial by 100 or something. Right, so there's a direct relation between this correlation and the mean squared error that I talked about earlier. And so this is sort of the goal. Now the goal is to you know, show that this thing is little of 1. Does that sound plausible? So the first attempt at this might be to just kind of, you know, directly write it all out. Like, what is the numerator and denominator of this thing? The first claim is that the numerator is some linear function of the f hats. Right? If I kind of write out what this is, you can think of it as being the inner product between f hat, right? F hat, thinking of it as a vector whose entries are these coefficients. And you know, inner product between f hat and this c, where c is some other vector that has these coefficients. Right, so c is some explicit thing that you could compute. And then similarly, okay, what's the denominator? So this, you know, this thing inside the square root is something that's quadratic in f hat. If you similarly expand it out, you can write it as, you know, f hat transpose p times f hat for a certain matrix p, whose entries are these. Okay. And so, you know, great, let's just kind of explicitly try to solve this then. So the correlation is equal to, you know, maximizing over f hat of this linear thing divided by this quadratic thing. And, you know, great, this has just an explicit solution. So it would seem like we're maybe in good shape, but the problem is that this p inverse is not easy to handle, right? P is some explicit, you know, but complicated matrix. And, you know, finding the inverse of this matrix explicitly does not seem like a tractable thing to do. So really, we're going to have to try to apply some tricks in order to still get an upper bound on this thing, but in a way that's, you know, kind of tractable to work with. Okay, and you know, some of the difficulty here is coming from the fact that these t's we're using, you know, these t to the d monomials are not orthogonal to each other. Right? If we had some, like, if these t's were kind of an orthonormal basis, meaning that meaning that these correlations are either 0 or 1, depending if d is equal to d prime, then this p would literally be the identity matrix and we'd be in good shape. Okay, so let me try to tell you what to do instead of this. So, you know, like we've talked about, our algorithm is a function of t, the thing we observe, and we can expand that, you know, in the coefficients f hat. But remember, the t is the sum of these a's. And so for any f of t, there's sort of an associated g of a, right? If I just think of t, you know, think of f as a function of a instead of t, right? And a is really the r different entries a1 through ar, so it's a multivariate polynomial in the a's. And this again you can expand, right, in some standard basis. So here we're using just these like kind of standard parity Fourier characters. Is that okay? And okay, why are we doing this? Well, it's going to be crucial that these basis functions, right, a to the u, you know, these are actually orthogonal. These are kind of the standard, you know, Fourier basis, and they do have this orthogonality. And so we're going to try to like leverage that orthogonality when we do the proof, but we're going to also have to kind of work with both sides of this and sort of go back and forth a bit. Okay, so why is the orthogonality helpful? Well, you know, part of the difficulty was understanding this denominator, right? Expectation of f squared. But now we can write expectation of f squared just as expectation of g squared, right? Because f and g are the same. And then by sort of like Parseval's theorem, you know, because of the orthonormality, this thing is just the sum of the squares of the g coefficients. Is that okay? So that will be crucial. But of course, we're also going to have to handle like how are the f hats related to the g hats, right? How are these coefficients related to these ones? And what I claim is that there's some matrix relating these. If I take any f hats, I take some polynomial here, I can plug in this definition, expand it out in terms of the a's, and that will give me some g hats. And this actually is a linear transformation that goes from the f's to the g's. Okay, and here's kind of the key, key sort of strategy that we're going to do is it suffices to construct a left inverse for this matrix M. Okay, left inverse meaning this like, M plus that has this property. So here's why that would suffice. Right, this was just the thing we started with that we wanted to control. Now I'm just plugging in this first claim on the bottom, right? This thing is equal to g hat squared. That's what I'm doing here, but I wanted to write it in terms of f hat, so I'm writing m times f hat instead of g hat. And the numerator is, we talked about this before, that is just a linear function in f. Okay. And okay, now I'm going to just like sneak in a copy of the identity up here, right? This is using the left inverse property. That's just the identity. And now here's kind of the crucial step. I'm going to replace mf by g. But this is an inequality now, because I'm now going to optimize over all vectors g, not just the ones that are in the image of m. Right, so I'm kind of relaxing the problem here and saying that this thing that used to be m times f no longer has to actually be in the image of m. And once I do this, now you have kind of an explicit solution, right? This problem is sort of easy because it's just saying like maximize the correlation between some vector and my g hat. And so you should just set g hat to be equal to that same vector, and that's why you get this. All right, so that's hopefully wasn't too much to follow. Any questions about this? Okay, so that's kind of one of the key claims, is that it suffices to construct an explicit left inverse for this M. And if we do that, we get some bound on the thing we wanted. Of course, different left inverses may give different bounds, and we need to kind of pick a good one, it turns out. Okay, but why should you be able to construct this left inverse, right? Like I told you a bit earlier, that inverting some matrix is, possibly quite difficult. So why should I hope to be able to do this? So let's just recall what we're trying to do here. We had some function of t, where t is the sum of the a's. You can think of it both as a function of t and a function of a. And so M is the matrix that relates these, and we want to invert this, or have a left inverse for this. So in other words, what does a left inverse mean? It means if I take any f, I apply M in order to get the corresponding G, then this left inverse is the thing that takes in G and gives me back F. Right? In other words, this problem of constructing a left inverse is really the problem of, given a valid G hat, recover the original F. Right, where valid means that it's actually a G that is of this form. It actually came from some function of T. Right, like if I give you G is equal to just A1, this would not be valid, right? There's no polynomial in T that would be equal to just A1, right? In particular, the valid G's are all very symmetric with respect to all these variables, because they come from some function of T. Is that okay? And so that's now the last thing I kind of need to convince you of why this should be possible. If I show you a polynomial G, that's a polynomial in A, can you figure out what polynomial of t it came from? Right, so let's do kind of a proof by example to illustrate why this should be possible. Right, so let's say R is 4, D is 3. D is the degree of the polynomial t here. Right, so I show you this polynomial in G or in A, right? Looks like this. And my claim is that this is actually equal to some polynomial in the sum t, and your job is to figure out what it is, right? Okay, so what are you going to do? I mean, maybe you look at this first term and think, how could this first term possibly have arisen? I mean, the degree of my, I'm given the degree of my polynomial is 3, so there aren't too many options. Like basically the only way this term can arise is from raising this thing to the third power, right? If I raise it to a second or first power, I'm not going to get 3 things like this. So this first term here is sort of a giveaway. It tells me I know actually that I must have had a certain multiple of t cubed in my original polynomial, right? Because that's the only way to get this term. And I specifically must have 1/6 times t cubed because that's what you need in order to get that term to come out, right? And so I can now expand out, raise this to the third power, expand this out, remembering that the a's are plus minus 1s, so that's why you get some lower terms and stuff. And so now I know this term must be included, so I could sort of subtract this off and then keep going. So it turns out there will always be, one term you'll see in your polynomial that's like kind of a giveaway that, oh, this means I must have had this particular monomial in F. All right, so hopefully this makes a bit of sense. Any questions about that?
Is it kind of like a Grosvenor basis calculation from polynomial?
Yeah, that's a good point. I don't exactly know the relation to that. I mean, maybe this is even simpler than Grosvenor bases somehow because Grosvenor bases take double the exponential time to compute or something, whereas this is something you can actually write this entire procedure of inverting. You can actually write this as just a single linear operator.
I think it's because it's the Boolean case.
What was that?
I think it's because it's the Boolean case, so it's multilinear. It seems to me like that's one way to think of what's happening.
Oh, interesting. That the Boolean case makes this easier.
I don't think it's just because it's Boolean. You're just eliminating from the top degree.
On one side than the other, right?
I guess we could talk about reading.
I think you're just eliminating from the highest degree term.
Yeah, but I think that's all. Anyways, I think that's all the Grosvenor case.
Oh, I see. You're saying that the number of terms could blow up. Ah, okay.
Yeah, that's a good point of the potential connection to Grosvenor bases. I should think about that. Okay, so I know we're about out of time. So just to conclude this lower bound, what have we shown now? Following all these steps, we managed to bound the thing we wanted by some explicit thing involving a explicit left inverse we were able to compute. So at the end of the day, the bound we get is the norm of some particular vector. It turns out you can carry out this same procedure for the real, not for the baby problem, but actually for the actual tensor decomposition, largest component recovery problem. And so in the true model, what ends up happening is, what these V's are, because of this kind of recursive structure of the M plus, you get some kind of recurrence on hypergraphs. So, this V ends up being indexed by hypergraphs, and the way you compute a V value is by kind of thinking about ways to collapse the hypergraphs to smaller ones. So, this is A is some particular hypergraph. here's a picture of the same hypergraph. Ignore the colors for a second. And so if we want to compute, the value for A, we have to think about all the different ways to collapse A to a smaller hypergraph by XORing some edges together. Right, so in this case, I'm taking these two orange edges and XORing them together to make this edge. In this case, I'm XORing these orange edges together to make this one. And so, the recurrence is something of this form where you get, coefficients times the values of these like smaller hypergraphs that you compute. So you have to think about all the possible ways to reduce this to a smaller hypergraph. And these alphas actually can have both positive and negative signs. There's quite a lot of actually subtle cancellations going on in here. And so understanding how this recurrence behaves is the most like difficult and, technical part. But, I won't try to get more into it than that. All right, so that's basically it. So just to sort of sum up, this was kind of the first concrete lower bound for random tensor decompositions, giving some concrete reason to believe why you should not be able to improve the current best algorithms. I talked about order 3 tensors today, but really the same result holds for any odd order, at least 3. And the threshold is, actually n to the k over 2 in general. Okay, so there are a few natural extensions that one could do, like considering the even k case, maybe doing Gaussian components instead of Rademacher, making the upper bound polynomial time. And maybe, these I expect should all be approachable using the same kinds of techniques. I think I'll just end by saying one, open problem that I think is kind of very interesting is about not random, but generic tensor decomposition. So I showed you that this was sort of the, the situation for random tensor decomposition. We have this easy, hard, impossible phase. But now what if I want to weaken the assumptions and, I just want, instead of the components being random, I just want them to be sort of sufficiently generic, say linearly independent. Or more generally, belonging only some measure 0 set of bad components are sort of disallowed or something. In that case, we actually don't really know the answer. So we only know algorithms in a smaller regime. We only know algorithms when the rank is up to n. And this remaining part here is totally open. So here I'm not even sure what to conjecture about, whether there should actually be a better algorithm or whether there's sort of an inherent gap between the generic and random problems or what. But I think this would be a really interesting question to resolve. All right, so yeah, thanks a lot for your attention and happy to take more questions. Thanks.
Any questions?
Say a couple of words. What goes wrong for even order?
Oh, not much goes wrong. It's just that the problem formulation needs to be set up a little bit differently because you can't hope to actually recover the vector A1. You can only hope to recover it up to sign. So like if it were A1 or if it were negative A1, you wouldn't know the difference because we're doing like an even tensor power. Does that make sense? And so the goal should not be to recover A11, right? That's like impossible. Right? I mean, the lower bound still holds. It's just not interesting.
Okay.
You should really try to recover maybe A11 times A12 or something like this to break the symmetry. Does that make sense?
Yes, yes, makes sense.
So one question, I'm not sure it'll be easy to answer this, but I didn't see where the n to the 3/2 came in exactly.
Yeah, right. Yeah, it's not clear really from here. I mean, it comes from analyzing this recurrence on hypergraphs, basically. But yeah, I don't know if there's really there's nothing kind of simple I can say in one sentence about where it comes from, unfortunately, I think.
And even also on the upper bound side?
on the upper bound side,
Required that.
right. I mean, it again kind
It
of
didn't say much
comes,
about it, so.
yeah, it again kind of comes from some, when you analyze these tensor networks, you end up having some kind of combinatorial counting arguments, and it comes out of this. But yeah, I think there's not like a super transparent reason why that threshold comes up, I think, as far as I can tell.
I don't know if this is just, yeah, just lucky, but or random correlation, but for end of the three halves also comes up for like resolution lower bounds for random 3CMS.
Yeah, that's true, right.
Same reason.
Yeah, right. I know you mentioned also the Feige thing earlier, which I guess is related to that. Yeah, that's a good point. Like I don't know of any relation between these two, but right, it is kind of suspicious that they're
But-
related. Yeah.
Isn't that more similar? Random 3CNF isn't more similar to maximizing computing the tensor operator norm of a random tensor, of a Gaussian random tensor, rather than tensor decomposition.
Yeah. That's what I thought. So I'm not sure if it's connected at all.
I mean, the analog tensor problem, and actually, if you take random, for instance, if you take random tricks or SAT and you do max XOR,
Right.
is, for large degree is similar to maximizing, computing tensor operator.
Thanks very much.
Yeah, thanks so much. All right. Great.
Thank
Any
you.
other questions? Or...
No, I've been, I'll let somebody else in. Thanks a lot, Alex.
Great. Yeah. Thank you. All right. See you later.
Bye-bye.
Thank you.
Thanks a lot.